Good afternoon, everyone. We're really pleased to have you here for our last research exchange talk of the semester. My name is Camille Crittenden. I'm Deputy Director of Citrus, and we want to welcome you here for this weekly seminar series, and also to welcome our web viewers. The program is webcast live to people in their living rooms and offices, and will also be available on our website on the YouTube channel following, so you can go back or refer your friends to it. Thanks for joining us for lunch. Those of you who were able to register in time, everything is compostable, so feel free to use the bins in the back of the auditorium for what's left. The series will start again in January, and I just want to take the opportunity to thank our series curator and coordinator, Yvette Subramanian. I don't know that she's in the auditorium at the moment, but she's done a great job this semester, as in all the previous semesters, in lining up some really fantastic speakers that represent the breadth and the depth of what Citrus has to offer. So I want to give her good recognition for that. Next week, next Thursday, December 15th, we'll have a couple of special events here in this auditorium. We have the Citrus Town Hall at 2 p.m. We'll have some remarks by our director, Kostas Spanos, and then we'll have a special guest in the Executive Vice Chancellor and Provost, Carol Christ, who will give remarks about Berkeley and how changes in research here on the Berkeley campus and at UC overall might have an effect on Citrus and the Bonato Institute, and will be available to answer questions. After that, immediately following that at 3 p.m., sounds a little bit in and out, right? At 3 p.m., we'll have a holiday celebration, the Citrus holiday party just out in the atrium. So I hope you can join us at 2, and then I hope you can join us at 3. There is a place to register online, but if you can't, just feel free to come by as well. So we're really pleased to have Mickey McManus here to speak with us this afternoon. He's got some really interesting material to share, and I'm sure we'll be grateful for our feedback and thoughts as well as he's developing his ideas. He's a research fellow at Autodesk in the Office of the CTO, and principal and chairman of the board at Maya Design, a design consultancy and innovation lab. He's a pioneer in the fields of pervasive computing, collaborative innovation, human-centered design, and education. So all of those interests sound very well in line with Citrus's interests as well, and we're really delighted to host him this afternoon. Please join me in welcoming Professor McManus.
Thank you. Thanks. All right, can everybody hear me? Good afternoon, everybody. So I'm probably going to do this in about 3 parts. The first part is a little bit looking back at some of the work that I've been doing and thinking about around pervasive computing and the Internet of Things and things like that, the sort of world saturated with computing. The second part is what I'm doing right now, new research into a new book and some experiments I've been doing. And the third part is sort of maybe how we prepare for what's coming and what does it all mean. And maybe even thinking a little bit about what it means to education as well. So we'll see how we go, and then I want to open up for questions, and I would just love any feedback or questions. I'm sort of right in the heart of some research that I'm doing and some work I'm doing. So for the last 14 or 15 years, I ran a group that came out of Carnegie Mellon 27 years ago called Maya. And Maya stood for Most Advanced Yet Acceptable, and we were a sort of interdisciplinary team of cognitive psychologists, anthropologists, ethnographers, computer scientists, electrical and mechanical engineers, and designers, architects, et cetera, looking at sort of how we tame complexity. And our whole mission was that complexity was power, but you didn't want to necessarily just throw it all away, put the big red easy button on something, but you may want to tame it and actually make it fit so it's a natural extension of how people work and think and give them superpowers. So that's what we've been focusing on for 27 plus years. And in some ways, the way we did that was we looked at a big interconnected world, the massively connected world, the idea that we're never going to be in a world that's not connected, or at least it seems like we're on a path to a deeply interconnected world. That's the challenge. And then what are some antidotes to that challenge? What are some things we could do? And one of them was human-centered design, get more brains on deck and actually help shift from we can make anything and we can make it right to asking the question, what's the right thing to make? And the right thing for who? And should we do that? And what would be the appropriate use of those things? So human-centered design was one antidote to a deeply connected world. Another one was taking an architectural approach, not just solving for the tip of the iceberg, but really understanding the entire system below the surface and thinking architecturally about the challenges. So we can understand the things we could change and maybe understand the things that were non-deterministic or that were kind of out of bounds. What I'm going to talk about today, looking back a little bit, is some work that we did that led to a book called Trillions. And that was really focusing on the connected world and what's happening in that space. And so the topic of my talk today is what happens when products and places wake up. Because I think we're at this moment where the very nature of things is changing. The very nature of places is changing. And how do we prepare for that? So I and my two other partners at Autodesk, at Maya, created a book called Trillions, where we documented about 20-some plus years research into pervasive computing that we had been doing out of a lab that came out of Carnegie Mellon. And the idea was, could we write a field guide for an era of unbounded complexity, basically, a very connected world, a field guide for an area where it's a sea of information devices. What must be true in that world if we reached trillions of computing devices? And in the writing of the book, I learned a lot about sort of how do we tell stories about the research, because some of it could be pretty dry. And the first thing is, what does it mean to actually have trillions of connected devices or connected information devices? And so a wise man explained to me that a good way to think about really big numbers is to count back in seconds. And so I want everyone to count back in seconds and think how far back is like 1,000,000 seconds. So someone raise their hand when they know about 1,000,000 seconds. What do you got? So around 11 days. That's not so bad. So when you think about big numbers, it's kind of nice to put it in another context. So 1,000,000 seconds is like maybe a week and a half ago, so like 11 days. Now think a little bit about how far back 1,000,000,000 seconds is. And don't shout it out, because I figure you're going to have that one. But think about it and raise your hand when you have a sense of how far back 1,000,000,000 seconds is. We know about 11 days, a week and a half is 1,000,000. So how far back is 1,000,000,000 seconds? So raise your hand. Don't shout it out, but just raise your hand when you have an idea. Just a guess. And it could be a wild guess. It could be totally wrong. I got it wrong. So 1,000,000,000 seconds. I see one hand. I see two. Come on. Is anybody awake in there? Just give me a guess. All right. What do you got? A year. A year. OK. So how far back is 1,000,000,000 seconds? So the weird thing about how people think about things is we have really bad sense of numbers. So it was like the 1980s. This is around the time that Intel won this battle for the 8-bit byte. So there were multiple kinds of standards around how big a byte should be, and Intel got that. The 1980s, late 1980s. OK, great. So now we're ready, though. 1,000,000's a week and a half. 1,000,000,000's maybe the 1980s. How far back's 1,000,000,000,000 seconds? So raise your hand when you have a guess, and it's OK if it's wildly wrong. We could learn something from it. All right, I need to wait for a few more hands. Come on. 1,000,000,000 seconds. All right, you seem like you've got some answers here. What do you got? 30,000. Yeah, so if you're a mathematician, you just go, well, I guess I should add like a few zeros. And in the American way of framing trillions, it's actually a 1 with 12 zeros. And when I guessed, I thought maybe the 1500s. I was just wildly wrong. But it turns out it's about 30,000 years ago. So 1,000,000,000,000 seconds. And most analysts agree that we're probably going to have 1,000,000,000,000 connected or computational devices in the next 5 to 10 years. It's pretty big. That was like we were living in caves. We were trying to domesticate animals. How many people were close? How many people got 30,000 years ago? How many people had some wildly different answer? What did you have? 150 years. Yeah. It's just like, oh, I'm going to say 1 BC or something. Yeah. I know, and it's just because we're really not good at exponential growth. We're not good at this kind of stuff. But you have to frame it this way because you have to really think about what we're facing. We're fundamentally shifting from an era where information is in the things, like we look at our phone and we see our apps, or we look at our desktop and we see our folders, to us living in the information. Trillions of things sending maybe lots of information to us all around us. So a sea of information devices. This is how big it is. And I'm not talking about 1,000,000,000,000 $1 bills, because that would be easy. If we just had 1,000,000,000,000 of the same thing, 1,000,000,000,000 smart devices that were all the same, homogeneous, and they weren't connected or some of them weren't connected, I don't think it would be that big a deal. The problem is we're talking about 1,000,000,000,000 things that are sending 1,000,000,000 messages, 1,000,000,000,000 things that are turning into bricks when you give them a bad update, 1,000,000,000,000 things that maybe have a malicious intent. So I don't know, how many people remember when a very major Internet of Things company decided to put code in their product so that whenever it was tested by environmental protection agencies, it lied about how good it was as a diesel car. Anybody remember that? So that was a few lines of code that one of the best brands in the world, ostensibly, decided for years to put inside of their devices, and only turned on when it was being tested to see how good clean running it was. That's Volkswagen, Audi, if you don't remember it. And so this is the era we're talking about. This is an era of unbounded, malignant complexity. That's what the history books are going to call the real information age. We've been in the foothills. But this is what we're approaching. And this is what all of our students, all of our kids are going to be living within. And to give you a sense of that, and when we wrote the book, people kind of were like, yeah, sure. Did anybody remember maybe a month and a half ago, hackers took over 145,000 internet cameras, HP printers, Panasonic speakers, etc., and took down a Minecraft server in Europe. Anybody hear about that one? So a few people. How many heard about the next week or the next 2 weeks when they took down the directory for the entire internet and Netflix stopped working? Yeah. So the first test was in Europe on a Minecraft server, and it basically turned a bunch of these things into a zombie army. So if you're interested in doing this yourself, here's the list of usernames and passwords. You can do it yourself. Just take a picture of that, write some code. So this is the era we're talking about. Wall Street Journal had a really nice article. It was basically, this is what you should do. Turn everything off. That was it. And this stuff isn't just around us. It's inside of us. So Johnson & Johnson just got dinged because basically anybody could take over their insulin pumps with a little bit of code wirelessly from a few hundred feet away and inject a lethal dose of insulin. That's nice. Pacemakers as well. There are many pacemakers on the market. I think St. Jude Medical makes a pacemaker that they recently had a big hit on Wall Street because it was shown that within 50 to 100 feet, you can install code to give a 900-volt lethal shock. And these are pacemakers in our parents', sisters', brothers', grandparents' bodies. So in Trillions, we decided it would be really sucky if the entire book was just a pity party. It was just like, let's just give up. So what we did was we put it all in chapter 3. So if you ever get around to reading Trillions, that's where the Cry Yourself to Sleep chapter is. And the point of it was sort of scared straight. It was like, let's pay attention to what's happening because there are certain patterns that must be true in this unbounded world. And there are certain things we could probably do if we turn 5 degrees differently, but you better wake up and pay attention. Maybe at the end of chapter 3, run outside of your house after chopping it down and lighting it on fire and see how big the world is, because the rest of the book is really about the opportunities. In a sense, we're fighting over the last few inches of Billions Mountain, maybe. This MySpace has to die for Facebook to win. We think the web is the end instead of, the beginning instead of the end. Relational databases, all this stuff invented largely in the 1960s. I think Unix, which is on a lot of people's phones, was invented in 1969 by Bell Labs. C was invented in 1972. So this was when the idea that we would have trillions of things was just a pipe dream. That we might have billions of things was a big deal. And so we think that's the future, but really that's just the foothills. And a lot of times when you go and you climb a mountain, you get to the top and you realize you weren't even near the peak. That the foothill was blocking the bigger peak, and you confused a good view for a short distance. And this is, I think, what's happening. The good news is there's plenty of business and there's plenty of interesting opportunities on Trillions Mountains because it is so big. Anything multiplied by a trillion turns out to be kind of a fun number. McKinsey put out a report last year that said basically between $3 and $11 trillion will be contributed to GDP every year by 2025, just from the Internet of Thing component of trillions. So there's a lot of stuff you probably shouldn't have all connected to everything else. That's a monoculture, and it's basically begging for being attacked. But just that part of it looks like it's probably going to deliver a lot of value, just because you're able to capture the exhaust data that's pouring off of things and try to do better energy management or try to do better maintenance on the stuff. So I wrote that book, and I started wandering around and preaching about trillions. And I would go to Madison Avenue, and they would go, "This is amazing, but you don't know what this means to marketing." And Madison Avenue funds 90% of Google, so that's an interesting question. What does it mean to marketing? And then I would go to the Mayo Clinic, and they would say, this is interesting. What does it mean to healthcare? And then I would go to a very big car manufacturer, and they would say, this is amazing, but what does it mean to manufacturing? And I would basically have to say, I have no idea. I don't know. And I decided to take a little time and look at some of the other big megatrends. So if that's one big megatrend, a world saturated with information devices, what else is going on out there? And could I learn more and maybe start writing a sequel to Trillions that was focused on that? And that's my current research. And so I joined Autodesk as a fellow in the office of the CTO. How many people know what Autodesk is? Probably everybody. Yeah, a lot of people when I say it, they go, oh, AutoCAD, which is good. That's how it started, and it's a California company, so a lot of people here probably know about it. But probably about 200 products. 90% of all the buildings in the world are designed in Revit. I think every factory, piece of infrastructure, city is designed in InfraWorks. Half the products in the world and all the cars in the world are designed in it. And I think every movie in Hollywood that has special effects for the last 35 years, we've won an Oscar. Because we do that, although it's a small part of our business. But what was neat was they were focusing on digital manufacturing. And I really thought that probably a world saturated with computing devices would also change manufacturing quite a lot. And what I realized were there were at least 3, and probably more, big megatrends that are all coming together at the same time. Not just the Internet of Things, but also digital manufacturing. The idea that you could 3D print something or additively and subtractively manufacture something, or that you could do trade-offs between a software update and a hardware update is fundamentally different and new. And also, all these things have opinions. Because we have spare computation cycle and sensors to do A/B tests on their own, these things are probably going to be collaborators with us. So I started thinking of it as almost a primordial soup, not just a sea of information devices. So my new book is codenamed Primordial at the moment. And I think these trends are inevitable. This is just happening. And they're not independent, and if you look at them independently, you will miss some big patterns. So I think it's really important to look at these together and look at what they're enabling. So if I dive into the soup a little bit, this is sort of part 2. When I say Internet of Things, I think a lot of people picture things like the Nest and the stuff that we see in our home, the thermostat, the smoke alarm. Why do you think Google bought Nest? Anybody have any ideas? Data. Why? I mean, they have a lot of data. They're insatiable. Well, that's true. They're insatiable. Yeah, I would posit that the reason they bought Nest is they wanted to install an oil well between your living room and your kitchen. And they wanted to drill for all the data falling off your wall as exhaust that nobody's paying attention to. Like, that wall knows a lot of stuff. It knows the humidity as well as the temperature. And humidity actually affects how we feel about temperature. It knows if Bobby's checking the fridge because it's got a motion sensor. It knows all sorts of other things, and I think they wanted to know in context what your life was. And when you install this, you sell the house, the next person gets it, so they're going to get like 15 years of data. So they wanted to capture the exhaust data pouring off of things. When I think of the Internet of Things and I think of sort of the primordial world, I think of things way more boring. And certainly that's going to help us maybe manage energy costs and things like that. That's going to give them an owned piece of media in your house, too, which means they don't have to go through anybody else to talk to you. They can go straight to the device. I want to show you a little video clip. It's just a short snippet of a larger clip of an Internet of Things device that is also using machine learning and sensing and is evolving pretty quickly. And it's kind of curious. This came out of Carnegie Mellon research. And it's just a lowly headlight, just a headlight. So take a look at this. It's evolving pretty quickly.
Driving at night during a snowstorm is a nightmare. Snowflakes appear as bright flickering streaks and are very distracting. The problem is mainly caused by light from our own headlights reflecting off the snowflakes back to our eye. The solution to this problem is very simple with our headlight. By avoiding illumination of the snowflakes, in other words, streaming light in between the snowflakes, the visibility of the snowflakes will be reduced. This might seem like a crazy idea, but preliminary experiments with artificial snow demonstrate that it is technically feasible while significantly improving visibility with little loss in light. The current prototype is 10 times faster than our previous prototype, with much better performance, bringing this technology closer to reality.
So what's curious about this is the new version that I saw recently. They had 60 cars coming at this car. All of them, this car was actually putting a black pixel over the eyes of the oncoming drivers so that the drivers didn't see high beams coming at them. And yet the road ahead was totally illuminated. And in fact, it automatically illuminated like a deer walking across and a bicyclist. And what it was doing was it's a DLP projector with a camera and mirror system so that it can see ahead, do some machine learning, learn to get faster and faster. It's communicating with all the other headlights, too, to try to get better at this. And it's basically putting black pixels over things like snow so you don't get internal reflection, and over things like rain. And it's just a really simple, boring example, though, of what happens when things are designed with this in mind, when we actually have things that can kind of be, in a sense, learning and evolving with us. Another way of thinking of the Internet of Things is all this stuff. Oh, go ahead. Yeah. That's a great question. I mean, it'd be worth looking up. I can tell you the name of the researchers. But Takeo Kanede is the main researcher there. You know, I think they were literally off-the-shelf projectors, but they built a new little housing with a mirror and a camera. So I'm going to guess they were like whatever the current state is. And so, you know, it was just good DLP projectors. What's fascinating is actually watching this thing in action turned on and turned off. Because the idea is you never turn on your low beams again, right? It's just always high beams for you. And it's never blinding anybody else, because they could approximate a driver's car coming at you has 2 headlights, so your eyes are probably about here, so they just put a black spot right there. And they're able to do that very quickly. I started an educational institute a while back, and one of the founders, Chris Passione, his previous company with a guy named Astro Teller was something called Body Media. And Body Media is interesting in that they took tens of thousands of dollars worth of medical equipment, hundreds of thousands of pounds worth of stuff, you know, all the blood ox stuff that you might see in a rehabilitation center. They tested a whole bunch of people with all these sensors to see what happens with how your body works. And they boiled that down into like $50 worth of sensors. And they put it right here, and they called it a body bug. And they replaced all that mass with math. And they started doing this with hundreds of thousands of people testing this stuff. They ended up getting FDA approval and clinical proof that they could help you lose weight. Their idea was media was pouring off your body. And if we could capture some of that media, we might be able to discover the owner's manual. You know, and what was curious about this is they had 6 sensors, a few 100,000 people. They collected 500 trillion data points. And so they started to kind of see this media pouring off your body if we could actually detect it. I've got another example here. It's a little project I've been doing at Autodesk where I said, what if 3 kids in a garage could start a car company? The same way 3 kids at a dorm room started something like Facebook. In the media space or in the internet space, could you do that with manufacturing? And so another example of Internet of Things is something called reality capture. So I want to show you an example of what reality capture looks like. And you guys are probably pretty familiar with this, but it's this notion that you could have sensors that could actually do photogrammetry and other things, and do them casually so that you could be capturing stuff all the time. This is using a laser and a camera, and it's scanning and ripping a very high-end racing car that's used out in the desert. These are guys who design cars that win Pikes Peak and Baja 1000. And we ripped, basically, the car, and then we also use sensors to do some other things, like take that into a program, put Internet of Things sensors on, and this was all done with a bunch of interns. And then take it out into the desert and beat the heck out of it so we could actually capture the reality of both the phenomena of the stresses, like the stretching of the metal on the chassis, the flow of organic compounds from the front to the middle to the back of the car, as well as sort of just all the forces. And we said, what if the car itself was participating in its own redesign? What if it was continually telling us this? Not just some samples from the biggest car companies in the world, but what if it was casually that you could literally almost put these sensors everywhere and test things? And we also tracked EEG. So we used Emotive, a local company here, $200 EEG things. This is their high-end one, but they have a low-end one. And we tracked attention levels. We tracked valence with task. We tracked what the driver was thinking, because the driver is a part of the system as well. And he might be hearing something that he actually gives him a predictive ability to know something that we weren't able to capture in some other way. And so then we were able to kind of take all this data and kind of put it all together. So this is like, I think an afternoon, we captured 4 billion data points. And of course, the interns came back and said, great, Autodesk, what can open this? And what can you do with it? And it turns out we don't actually have many products that can do much with it. Although, if you think of simulations in general, every bend of a triangle in a mechanical simulation is actually like a sensor. It's sensing the bend of the triangles. So we took that and we looked at all the different kinds of elements that we could have, and we contributed that into being able to kind of understand what he was seeing. And we took that, and I'll show a little later, and we put it into a generative design system to be able to basically evolve a chassis from the forces. And when I mention evolving a chassis, we get to digital manufacturing. So if we talk about digital manufacturing, A lot has changed in the last few years with digital manufacturing. Most people think of 3D printing, but it's actually a fairly large range all around robotics, really. But synthetic bio, robotics, digital manufacturing, new kinds of materials. Here's an example of an experiment we're doing with Joris Laarman in the Netherlands. And the idea is, could we do free-form assembly and printing with traditional off-the-shelf robots, but just slightly smarter heads that were doing some computer vision, that were looking at the heating and cooling and things like that. This is a series of experiments that are all building up to be able to basically print a bridge when you just put 2 robots on the side of a bridge and hit go, and the bridge basically weaves itself and climbs over the bridge. So this is an example of sort of what happens. In fact, this is the bridge. It's in Amsterdam. And they're currently on track. They printed test sections, and they're currently on track to kind of get that happening. So digital manufacturing is changing quite a bit, and it's opening up opportunities that we never really had before. And I could probably bore you to death with all the different things that are happening in digital manufacturing. But a funny thing that is happening is the rate of change of manufacturing is changing pretty dramatically, too. So I just met some guys out of Italy who said, what if 2 billion people already have a 3D printer, or maybe half of a 3D printer in their pocket? And what if the other half of the printer costs $99? Like, what would that be? Because these kinds of printers they're talking about, photopolymer printers, usually cost about $8,000. And 5 years ago, they were $250,000. So this is what they're doing. They did a Kickstarter campaign, asked for about $150,000, got $2 million in the first 30 days. They are shipping these in January. I ordered 2. But you set it on your phone. You can imagine setting it on an iPad Pro and having multiple build chambers and being able to do like the soft parts here, the clear parts here, et cetera. But this posits a really challenging question because those materials are kind of dangerous. It turns out that all photopolymers in their liquid form cause mutation in fish, genetic mutations in fish. That's not a great thing. And so one of the big things they're going to have to do is pursue pretty aggressively what happens with materials science. And they are, I don't know fast enough. At Autodesk, we have a synthetic biolab where we're actually able to prove that you could create photopolymers, liquids that catalyze with light, out of chitosan, which is basically ground up seashells from like waste from the food industry. And we were also able to show that it was able to be made from stuff that you find at a health food store, and collagen as well. So I think there's a lot to be done in material science right now. I mentioned the Internet of Things and digital manufacturing. I think these things are coming together, too. So this is an $8,000 printer that's being put out from some research around high conductivity paste at Harvard. And what it does is, as it's printing, it says, hey, could you put in a circuit board? And then it keeps printing, and it says, hey, could you put in a battery? Could you put in a motor? Could you put in an LED? And it builds a 3-dimensional circuit within the actual shape. And then at the end, it says, hey, go grab your remote control. Let's go. So that's 2 of the trends coming together in interesting ways, right? So we're slowly moving from dumb material to slightly sensed material to material that can have some performance characteristics to maybe networked material to computronium or something. I think that's the path we're on. And that was a toy. It's kind of interesting to think about just big industries in general. Barbie's a $2 billion industry, and there are about 300 grams of plastic in every Barbie. And that means you can fit, I don't know, maybe 13,000 Barbie dolls in a shipping container. And actually, right now, global shipping is sort of almost at a standstill. There's a lot of challenges getting stuff through the docks. If you just sent the polymer and you manufactured it locally, you could send the equivalent of 250,000 Barbie dolls. So it might be that the economics of making something on the other side of the planet and then shipping it over here collapse at some point when we get to a phase change here. The third and last kind of big mega trend that I think is going to be impacting us quite a lot is that all these things have opinions. According to Andrew McAfee and others, we sort of crossed the magical second half of the chessboard in terms of computational power in about 2008. And now we're starting to see some amazing things from machine learning. So when I say machine learning, a lot of times you think about something like the self-driving cars. Everyone's seen them around. Mercedes had one. I think Audi had one that drove 500 miles between here and Las Vegas. Google's put a ton of miles on. It's really important. Well, obviously, Mercedes wants you just to have a drink in the back seat. There's no front seat. But what's really interesting about this is that whatever's in a self-driving car today is in your shoes tomorrow. That's Moore's law. And when they're connected, that's Metcalfe's law and Moore's law coming together. And we're going to have some really interesting things coming out of this. So QUALCOMM, you guys are probably familiar with things like the 0th chip. They put basically machine learning on a chip. It doesn't even have to connect to the internet. And you don't write any code. You just give it good robot or bad robot. So you basically just raise it like a child. You really shouldn't use sticks, but they certainly give carrots. And all learning occurs in this product with biologically realistic neural networks. It's like a $10 chip. And so the cost is moving down. And when we look at design and engineering, we're actually starting to apply some pretty significant machine learning efforts. Probably at Autodesk, we're investing, probably the largest part of our research dollars are going towards machine learning to actually help with design and engineering tasks. And so I'll show you one example. It's called Dreamcatcher. And what you do is you basically say, these are the fixed points. Maybe this is a port because it's kind of an axle between the swing arm of a motorcycle and the body. There are so many newtons of pressure coming from each place. Could you evolve a series of children based on the forces? So form follows forces. And as we put the pressures on there, we can actually look at millions of variations. We can slide a slider and say, I want it out of titanium, I want it out of aluminum, I want it to be manufactured within 5 feet or 5 miles or 500 feet. And it starts to evolve. And curiously enough, they start to look like, I mean, this particular one looks like a horse's hips. And it's kind of interesting because probably a horse's hips evolved through form follows forces. Here's that car that I talked about. We took all that data, 4 billion data points, and we brought it into Dreamcatcher, which is this tool. It's a generative design tool or a goal-directed design tool. And we started looking at what would happen with the car. And this was kind of interesting as well. So we went from car designers who started out doodling and sketching and thinking about things. And these are people who have won Baja 1000 races, who have built cars that have jumped football fields. These guys live on the edge. And we took all the forces that we captured out in the Mojave, and we actually started using Dreamcatcher to evolve, based on the forces, different things. And we basically said, I want to hold the material the same. This is chrome moly. We're not going to change the material in this one. We just want to see what would happen. Could we reduce the weight, and could we keep the structural integrity, or maybe increase the structural integrity of it so that it's more resilient? This is the final chassis that came out of all the different choices. And then we were able to go in there and actually say, send it off to an automatic fabricator that takes all the outputs and basically auto cuts all the pipes, auto laser etches all the elements, automatically bends all the pipes, and automatically numbers everything. Because if you were to look at something like that, that looks fairly insane to try to make by a traditional fabricator. And we could have used, like, titanium printing or aluminum printing, but those are pretty far out there. And we wanted to say, could a normal shop be able to assemble this? So after it was sent off to this automatic system, it was shipped flat packed to a shop in LA, and they assembled it in a week, like Tinker Toys, and welded it together. Now we're taking it back out again, and we're going to be testing it to see how the math worked. And this idea that the car could participate in its own redesign, that it could be a player in this, that it might even have machine learning running on it the whole time, I think is a fundamentally different approach to thinking about this. It is a participant. It's striving the same way when you plant a seed for a tree. If it hits a rock, it doesn't give up trying to be a tree. It goes around the rock. It builds it into its structure. So what happens if products start aspiring to their better selves over the course of time? And I think it's fundamentally a different approach. The other bit of machine learning stuff we're doing is using convolutional neural networks to actually scrape through all the objects that have ever been built in any Autodesk product. So you can imagine that Facebook has a social graph of your friends, and Google, I guess, has the graph of connections and links. LinkedIn has the graph of your careers. What if we could have a graph of things? And so we decided to do that. And because we have the largest body of things right when they're created, we started raising a child, a convolutional neural network, to understand thingness. So cars are mostly made of axles. They have some other stuff. It automatically assembled part groups. The part groups could tell us about things. These gears usually go with those gears. Those bolts go with these bolts. So it became basically an autocomplete system for the physical world. And we call it Design Graph. It's actually been launched with one of our products, and it's going to be more widespread. But it's this idea that I could take a lot of information and raise a convolutional neural network to be a part of a team and to basically participate with us. And so what we're starting to see when these three big trends come together, I think, is almost over the last 150 years, we've set up these static equilibria. Think of it like holding a pool cue and just letting it settle down. We build our business model, we build our supply chain, we come up with the way we make things, and then we hope nothing changes. And it's a static equilibrium. It's very effective, efficient. But I think we're actually suddenly, just like life itself, we're suddenly going to be able to make trade-offs between a static equilibria and a dynamic equilibria. So think of it as the difference between balancing a pool cue on your finger. It's hard, it takes energy, you've got to move around a lot. And if you look at the kind of systems that you have to have in place to do a dynamic equilibrium, you've got to have like sensors, and you've got to look at the right thing. Looking down there doesn't help much. You've got to have a feedback loop with those sensors. Why don't we call that the Internet of Things? You've got to have the ability to change things, like 3D print something or send a software patch. And you also have to have the ability to learn. It just so happens those three trends are coming into focus. And so the minimum requirement for being able to do trade-offs between dynamic and static equilibria, I think, has just come into view. So I think there's going to be a lot of new value. And I think a lot of it is going to be actually learning how to let go. I think we're going to have to design for loss of control and become more gardeners out there, because the products are going to be evolving and co-evolving the same way grapes evolve based on the terroir of the land. The good news is McKinsey put out another part of the report said that most of the value in this big economic push is going to be in the interconnectedness. It's going to be in how we play together in an ecology of information devices. And I think that's really where we're going. And so to end this, I think I'll end on one last part. I think we're moving from one-size-fits-all tools to very much context-based and generative, from one or two careers in our lives to probably automation disrupting all jobs. It's probably a whole other talk there. From a very waterfall approach to design and engineering to some radical collaboration, maybe with machines as well. From monolithic manufacturing to social networks of fabs, from selling things to selling experiences, from users to learners, and maybe even some of the customers are going to be machines as well. And I think I'd like to challenge everyone to think about what happens when things wake up and how do we design ecologies? How do we have a system view of this stuff? Because I don't know if we teach system thinking very much, or if we teach it deep enoughly, or if we actually have anything between being a system engineer and being everybody else, but I feel like we need to. You know, ecologies and economies live on the edge of chaos. They allow for the freedom for agents to act on underused resources. That's really an interesting thing. And they need liquidity to grow and flow. So how do we do all that and put people first? I think that's maybe part of my question. And in terms of looking forward, I would say we constantly make and we constantly learn. And the act of making is teaching us a lot of things in the world. I think from an education standpoint, we may want to look at what this means too. You know, traditionally we go K through 12 or K through post-secondary, and we go to a job. And that system was built largely to kind of supply the Industrial Revolution. And it's a very if this, then that system. But life is actually much more messy. It's kind of like I worked at this place, I learned this skill, but nobody gave me credit for it. I had to put up with that boss. I learned this skill, but I didn't get credit for it. So what if we changed around the way we think of it and think of learners, whether they're machine or humans, and as they learn skills, maybe we've got micro-credentials running in the background that are convolutional neural agents too, that are kind of saying, well, you got that skill that opens up more paths. Well, you got that tool that opens up more paths. You worked with that team, that place. I'm noticing this pattern. That opens up more paths. You know, maybe there's a new skill. I noticed that this mindset changed. You learned about this. These things go together. That could open up new paths. What if, in fact, we started using machine learning to actually be a partner with us to actually predictively guess at new careers and what could be happening? I did a whole bunch of Instructables. That gave me a lot of practice. In fact, that identified something I don't even know, but maybe it's a new job in the future. So I think we're going to be shifting to a different form of collaboration. We're going to be thinking about machine learners and human learners probably in high-performance teams together, because GM is going to probably raise a different machine learner than Ford might raise. And the environment itself is all going to be contributing to micro-credentials, but not dumb ones, maybe machine learning ones themselves. And we'll be able to sense that stuff. I say learning environments, too, because we did an interesting experiment where we took an Instructable, which is just a way of building things, an online tutorial. One of our companies is called Instructables. And we said, what if we took a hard one, something you could hurt yourself with a Dremel, you could burn yourself with a soldering iron. And we tested how long it took for an amateur to assemble and build a proper thing and make it turn on. It's like an electronic thing. And then we lit up all the boxes with LEDs. We put fiduciaries on all the parts. We actually put sensors on the goggles so we could tell if you would put them on or didn't, if you turned on the soldering iron or not. What we noticed was a 47% reduction in expert interventions if the space itself was participating with the actual construction, if it was basically in context giving the right stuff at the right times. So I think we're gonna shift to a very different model, and probably those things, those places, and those other people are going to be guides along the way. I'm going to stop right there. We've got about 10 minutes left, but I just thought I'd leave you with kind of right where I'm at and sort of some thinking about how this might affect education. Thanks, everybody.
So we have time for some questions. I'll run around with the microphone if you'd like to pose something for sure.
Thank you. Very interesting. I'm reminded of environments in mythic times where basically everything was animate. You know, the stones had feelings, and the rivers, and whatnot. And we're getting to, you know, some kind of agency in the world that we're going to be interacting with. Have you thought about how this changes language? How this changes basically semiotic communication?
The short answer is not at all, although I love that question. But you know, I suspect it's been interesting playing around with things like Alexa and all the conversational agents, where you start to treat it like maybe your little brother or your little sister, or it's really funny when you have Siri set up with like Apple TV and Alexa and they start fighting with each other, you know, and it feels like you're just like, ah. But I suspect we're going to have an evolution of that too. I just think, in the broader sense, we're reaching this point where it's not about could we make something, we can make things. It's really about should we, which is a weirdly different question, and how do we use restraint? Because I think every single human on this planet, or many billions of humans on this planet, because of the lowering cost of all this stuff too, are going to have agency, and so are the things. And you know, I'm pretty sure at some point our 3D printers are going to start getting spam, and that doesn't sound good. I'm pretty sure that, like, you know, we're going to have to go through maybe some messy times to get to a good place. I'm not saying this is going to be easy, but I am really curious about how it's going to change society. I think the thing that scares me the most right now is we've lowered the cost of making complexity so much that anybody can make complexity. But we've had no conversations at all about managing installed ultra-complex things. And we have had no conversations on the policy front or anything, and I suspect we're going to muddle through, hopefully, but I'm nervous about that. I don't think I answered your question, because mostly I don't know, but it's a great thought.
You've given us a fantastic perspective of the future, how things and the world will be connected. And I really think there's this wonderful potential. Now, the bigger problems, though, that we face in society are not really, you know, solved by technology. It's of the layer above. You know, how do you reduce the income-wealth gap, you know, in our society? How to deal with the limited water resource of California? So, what hope is there that the same kind of trends that has these glorious futures for the Internet of Things and all of that, that we use some of these, you know, driving forces and aim them at our politics, at the way we control all of those things, which is really the key issue in a way that faces us. I think the things will take care of themselves, and you know. But how do we manage the more difficult problems of knowing what's the right thing to do, and then use that technology to actually do those things?
Well, so I think, I mean, there are a lot of things embedded in that question, and I love it. I would say, I'm not convinced that things will solve themselves. I think a lot of the mindsets that are taught in computer science and engineering and others are largely based on a scarcity model and on I'm the god of writing code and I can keep it all in my head and I can design things. And I suspect that if we look at nature, which a big chapter, a big section of our old book and the new stuff I'm doing is around biomimicry for information systems. If you look at nature, your body's mostly peer-to-peer. Peer-to-peer is a really nice pattern. If you cut your leg, it does not call the cloud to get it fixed. You die. Every cell in your body has a spare copy of you, and they all get together and start forming scaffolding. And then there's a layer of complexity, layered complexity. That's another great pattern in nature, you know, that is the endocrine system or the circulatory system or things like that. Most of what we're building is incredibly monolithic, and nature abhors singletons. So we go, yeah, you know, Google will figure this out, or somebody will figure this out, but there's no copy of Google. There's only one Google. That's a singleton. I could kidnap Sergey Brin's niece or nephew or somebody and have more power than kidnapping a president's daughter or son. Because there's only 5 clouds, and they don't work together. So, I mean, there are some fundamental things that I think we're going to have to grapple with on the tech side. I think right now the techs are running the asylum, and it's sort of gee whiz. They want everyone to learn how to code. I hate the idea that everybody has to learn how to code. I like the idea that we could go on with our lives. But aside from that, I think coding to learn is really fun because you get to see the insides of the world. You get to understand complex things. I think learning how to do something like a 3D printer and make something yourself, I don't know that I want them all to become engineers, but actually learning about that teaches you about supply chains and materials and how hard it is and things like that. So there's a meta, I think, literacy that's coming up that's kind of curious. On the political side, I don't know that I can comment much, but I do think if this were a can of Coke, and I picked it up and I saw that I lost 4 years of my life, I put it back down. If there was like a system sense, if I could feel like the feedback, right? And machine learning gives us prediction power at a very low cost. I think it's going to be very hard for us to fool ourselves about certain things. We always will because we're good at that. But I suspect if we have enough sensing from enough different flavors and enough different provenances so that they're not all able to be taken over, and in a much distributed way, I think it will be harder to hide from what's actually happening. And it'll be harder to hide from the predictions of what's actually going to be happening. And I think a lot of politics and a lot of this stuff is people asserting this policy will change this. But I suspect with the kinds of rise of this technology, we might be harder to hide. Now, we've just gone through a sort of post-truth revolution in politics, so I'm not sure if facts matter per se.
But who puts the chip into the Coke that tells you that you'll lose 4 years ago?
Well, yeah, that's it.
Somebody else puts a chip in there that says the contrary.
I think this is. I think every one of these things is potentially like a cargo cult leader too, right? It could, just like Richard Feynman talked about cargo cults and the danger of trying to understand science, a shaman who knows a little bit more than the average tribesman or whatever can co-opt. And I think we'll have products co-opting us too. So I totally agree with that. But we have to at least have that conversation, I think. And I'm open to that. I wish I knew how to address those things. It's a very complex world.
I'm curious, what's your goal here? What's the objective of this research? Did you start out with a theory and you're trying to prove it, or what's the end game as you see it here?
I think I started as a product designer. I started trying to understand what the future of product design was, industrial design and sort of this massive world that we fuel by kind of taking raw materials and turning them into something desirable or whatever, driving some economies. I think over the course of the research, though, I've really tried to understand how we would survive and thrive in this world. And my question is, maybe how could we get to the point of having a system sense? So my theory is, I think we need a new kind of sense. Because right now, we can't look at a system and tell if it's non-deterministic, if it's very dependent on initial conditions. We can't pick up a can of Coke and feel what it feels like to lose 3 years of our lives or something like that. We just don't have that kind of sense. I think today, most of technology amplifies our blind spots as well as our weaknesses. You know, I think Columbia University did a study that 60% of articles are retweeted without anybody reading beyond the headline. So we're amplifying blind spots, and I suspect that at some point, my theory is we could have a system sense. We could have something, not just system engineers and glorified priests, but that everyone could have some new way of feeling if something could be even fixed or not.
We have a system sense, and that's the nature of some of the questions that have been asked already, is if you're trying to create this robotic, technological sense, excluding the human nature that exists in making decisions, then your research isn't including that, is it?
Yeah. Well, I think probably it would be easy to look at the work that I've just gone through and say, wow, he really loves technology. But having been at Maya for 15 years or 14 years, where we were basically a bunch of cognitive psychologists and anthropologists and others, basically Luddites in most cases, but needing to cope with what the current state of the world is, which is complexity, and saying how could we actually put people first. I have a pretty strong opinion about having people be a part of this, but I also want to just flag what's happening, one way or the other. And I'm not convinced we have a system sense. I think we have a broken system sense, or maybe 4 people in the world have a system sense or something. So I don't know. It's an open, yeah, I feel kind of humbled the more I work on this. Because I get hit sideways in the head by things, and I realize the extent of what I don't know. But what's been neat is actually watching when I take in interns and others, and I just have them work on these things, how they start asking different questions. And maybe that's just always the case, you know. And that's maybe that's just part of the joy of this too. For me, it's just the aha moments that I wasn't expecting.
I'm just afraid that, as you alluded to, which you didn't know, is to what extent is the byproduct of all this the loss of something
else, yeah, some agency or some other, yeah.
The human element.
Yeah. Oh, I think yeah, I don't know. Perfect questions.
Thank you. So I think that's a good place to stop. And we really appreciate you coming to talk with us this afternoon, and enjoy the rest of your semester. Good luck and happy holidays.
Thanks, everybody.